Now, the first application we're going to look at for actual directional well planning is to build and hold to a single target. So we're going to build and hold to a single target, and so here is our target down here at the bottom, located here. We have a single target, and we're going to have 3 sections of directional drilling in order to go to this target. Many people forget that there's 3 sections. So there, if you think about this and write the algebra equations for executing this directional plan, we're going to have a vertical distance that we're drilling vertical with no inclination, 0 degrees. So you can look at this diagram and see, and then we're below that, we're going to have a vertical distance in which we're building angle. So we're going to be building from 0 degrees to some angle. And then we're going to hold that angle down here in the 3rd vertical depth section from whatever angle we get it built up to all the way to the bottom to the target. So we've got 3 sections of the wellbore. We're holding vertical angle, we're building angle, and we're holding angle. And likewise, we can write the expressions for the displacement. The displacement of section 1 while you're holding angle of 0, which should be 0 degrees, may not be exactly 0 degrees, but it's going to be close to 0 degrees, plus the displacement that you get while you're building angle, plus the displacement that you get while you're holding angle, has to be the target displacements and vertical depths. So that's a algebra relationships that really have to know. So these 3 sections again are from 0 to kickoff point. That's section 1, we're holding inclination at 0 degrees. Section 2 is while we're building inclination from 0 degrees to the necessary inclination of our downhole target. So that goes from our end of our kickoff point to the end of build. So that goes from a kickoff point to the end of build. And then the last, section 3, is the tangent hold section, in which the inclination is held at whatever we achieved at the end of build, and we drill at a constant angle inclination between the end of build to the target TBD. Okay. It's very important to understand you have three sections on even on a simple build and hold to a single target. Now, mathematically, there are infinite solutions to utilize in a build and hold profile, to drill a well to a single target. It's infinite. But the most common approaches are we select, number 1 is we select a build rate and a tangent angle. So let's just say we might select a build rate of 3 degrees per 100 feet, and then we may select an inclination of, say, 30 degrees. Really common to pick 3 degrees build rate and a 30-degree angle. And that one is what we would call an unknown kickoff point. So we've chose 2 of the 3 components, and we would have to calculate the 3rd component, which is the kickoff point. So this choice of choosing a build rate and a tangent angle, they've done for multiple reasons, but probably the 2 primary reasons is there's lots of experience drilling wells at this inclination and build rate with minimum problems executing a directional plan. So you may be developing a field and you're using, say, somewhere between a 30 degrees and 35-degree well and a 3-degree build rate to develop a field. And it works real well, minimal problems, and you've got a lot of experience doing it. And then the second reason is that inclination is easy to clean the hole and you minimize potential for having hole trouble. So The lower angle wells, you typically have less hole cleaning problems than you will high angle wells in terms of hole cleaning. So here are the steps that's listed out for you in order to calculate the kickoff point. So if I give you the build rate and I gave you the tangent angle, or you selected it, then you would have to calculate the kickoff point. So here's the process by which we would calculate the kickoff point. The first thing is you would calculate the value of the radius based on the equation. So if we chose a 3-degree build rate, you would divide 3 into 5730 and you would get a radius of 1910 feet. And then your second step would be to calculate the values of the vertical distance for the second section and the displacement of the second section while you are building angle. And you use the equations that we've already seen. The vertical depth while you are changing angle is going to be R times the differences in the sine. And of course, many people will say, well, you didn't give you the sine of angle number 1. I know sine of 2 is 30 degrees, but I don't know sine of 1. Well, we do really know. Sine of 1 is that the angle while you kick off is 0 degrees. That's by default. We assume a kickoff point is 0 degrees. So therefore, it would be maybe if you chose 30 degrees as your angle, it would be sine of 30 degrees minus the sine of 0. And then the displacement is R times the differences in the cosine of the two angles. So to calculate the value of D3, so we've just calculated D2, and we know what the total displacement needs to be. So in order to calculate the value of D2, it's going to be the total displacement minus the displacement that we calculated in this step, in step B. So whatever that displacement is, we'll need that. And then we can calculate the value of vertical depth in section number 3 by using the basic trigonometric function that since we've calculated the displacement in section 3, then the vertical height in section 3 is going to be D3 divided by the tangent of this angle that we calculated, that we have chosen, whether it's 30 degrees or whatever. And then, so since we have T3 and we have T2 that we calculated here in step B, then we can calculate our kickoff point. It's going to be the total TBD depth minus the T3 that we calculated in step D, plus, and then also subtract out the vertical depth that we calculated in step B here. So that would give us our kickoff point. So let's do an example here. Calculate the kickoff point for a well with a single target at 10,000 feet TBD with a 3,500 feet of displacement using a build rate of 3 degrees per 100 feet and an inclination of 30 degrees. I suggest that you pause your video at this point and calculate that value. It's the simplest directional plan we can do, so you should make sure you follow these steps A through E above and calculate a kickoff point. All right, the solution for this is based on, you can see that's very little information given. It doesn't take much information. You first calculate a value of R, which our value of R, dividing the build rate into 5730, comes out to a radius of 1,910 feet. Then in step number B, we can calculate the vertical distance and the displacement that occurs while we're building angle. And we plug into the two equations that we have in B above, and we get that the vertical distance while we're building angle is going to be the radius times the differences in the sine, which is 955 feet. And then the displacement is the R, which is 1910, times the differences in the cosine, which is 256 feet. So these are the values of true vertical depth that takes place while we're building angle. And then this is the displacement that occurs while we're building angle. Now, step number C is we got to calculate the remaining displacement that we need while we're holding angle. So the total displacement is 3,500 feet. We get 256 feet while we are building angle, so therefore we need an additional 3,244 feet while we are holding angle. So the TBD depth for section number 3 while we're holding angle is going to be this additional displacement needed, 3,244 feet divided by the tangent of 30 degrees, which is 5,619 feet. And then now we can calculate, we have all the information we need to calculate the kickoff point. So the kickoff point is going to be the total vertical depth, which is 10,000 feet, minus the vertical depth that we get while we're holding angle, minus the vertical depth we get while we're making our angle change. And so therefore it gives us a kickoff point of 3,426 feet. Now, I've shown there on the bottom that it's quite common to examine, the kickoff point with different angles for the reason that if I chose this angle and I chose this build rate and it gives me a value of 3,426 feet. But what if my casing point was at 4,000 feet? So in other words, if my casing point is 4,000 feet, it's going to require me to do directional work above and below the casing shoe in 2 different hole sizes. So I might consider, so for this example here, that if I were to use an inclination higher than 30 degrees, maybe say 35 degrees. So if I use an inclination of 35 degrees instead of 30 degrees, my kickoff point might go down the hole to 4,100 feet, and therefore I would only have to do directional work in 1 hole section below the casing shoe, but not above and below the casing shoe. So that's just an example of the considerations that you would make, I call it in the real world, to decide, do you think it's worthy, really important doing directional work in 2 hole sections, or you're just going to try to do it in 1 hole section. And then the second case that we can do for a single target is when we select a build rate and a kickoff point. When we do that, we have an unknown end of build. So we don't know how much hole section it's going to take to build angle, nor do we know what angle we're going to build to. So we don't know the angle. We just chose a build rate and a kickoff point. Now this choice is quite common, and it's done for these 2 reasons, to minimize hole sections that the directional work is executed in, thereby eliminating the need for different size directional motors and tools. And then this is a mistake on this slide here, but there's only 2 reasons. And then the second reason is to choose the shallowest practical kickoff point in a long reach well, thereby minimizing the hole sail angle. So the steps in the chart on the diagram below can calculate the sail angle number 3 that's needed to achieve this directional plan. So we can draw us a diagram, and if I draw a diagram to try to illustrate how we can do this work, then what we have is we have chosen the kickoff point, so we know the kickoff point depth, we know the target depth, and we know the build rate. So we know the radius, since we have selected a build rate and we have selected a kickoff point, then we can draw this diagram here, in which this is going to be the radius, and we can draw a line from the, I call it a compass point out in the earth, down to the target. And then we can also draw a line that's perpendicular. So this would be a perpendicular line with our arc that we're creating. And then we can calculate the value of this interior angle here, which is known as angle 1. And we can calculate the interior angle 2. And we can calculate the length 3. And we can calculate this additional displacement we need in order to come up with this sail angle number 3. So if we look at this diagram, L1, so L1, this length here, is going to be the target TVD minus the kickoff point. So we have a kickoff point here, and this length is going to be L1. So the angle 1 is going to be the arc tangent of this displacement B divided by L1. So displacement B is the target displacement minus R. So this is R here. This represents R. And so this is the additional displacement above R. And then so we can calculate, like I say, the displacement B. If the target displacement is greater than R, is positive, and displacement B is a negative value if our total displacement is less than R. That's the way the convention for this to work out. So the angle number 2 is equal to the sine of R divided by L2. So that would be the angle number 2. Now angle number 5 is plus angle number 1 plus angle number 2 equals 180 degrees. So in other words, these three angles must equal 180 degrees. So therefore, we know that to be a fact. So that we also know that angle number 5 plus angle number 4 is equal to 180 degrees. So therefore, we can see from this diagram that angle number 4 equals angle number 1 plus angle number 2. So since angle number 4 equals angle number 1 and angle number 2, we also can see that angle number 3 is angle number 4. So we can use the steps on this process to calculate this sail angle in order to go to this target if we choose a kickoff point and a build rate, which gives us a value for R. So we'll do an example of that. So application number 3 is calculate the sail angle for a long reach well to be drilled from a platform located in 300-foot water depth with a 100-foot RKB. The first conductor setting will be set 250 feet below the mud line, and the well can be kicked off with the directional assembly 150 feet below the base of the conductor. Plan to drill the well to its target located at 9,000 foot TVD with a 15,000 foot of displacement, utilizing a 3 degree per 100 feet build rate. I encourage you to pause the video and follow the example that we just went through and calculate the sail angle for this application. All right, going through the steps. The kickoff point is going to be the RKB plus the water depth plus the conductor depth plus the depth below the conductor. So that's going to be 100 feet, which is the RKB, 300 feet of water, 250 feet of conductor depth below the mud line, and then we're going to use 150 feet below that. So that's 800 feet. We could kick the well off, would be our kickoff. And our first step is to calculate a radius. So our radius, based on our chosen build rate of 3 degrees, is going to be 1,910 feet. So our displacement B is going to be our total target displacement minus R. So that's going to be 15,000 feet minus 1910, which is 13,090 feet is displacement B. L1 is going to be our target TBD minus our kickoff point, which is going to be 9,000 feet minus our kickoff depth of 800 feet equals 8,200 feet. So now we can calculate our angle at the top. O1 is going to be the arctangent of our displacement B divided by L1. So that's going to be the arctangent of 13,090 feet divided by 8,200 feet is 57.9 degrees is this angle 1 here. Okay, and now L2 is going to be the displacement of B divided by the sine of angle 1. So we've just calculated angle 1, and so we're going to be, we can calculate that by saying it's going to be 13,090 feet divided by the sine of 57.9 degrees is 15,452 feet. So that gives us L2. So we just calculated the value for L2. And now we can calculate angle number 2. Angle number 2 is the arc sine of R, this side, divided by this length, which is hypotenuse for that circle. So it's going to be the arc sine of 1910 divided by 15,452, which gives us 7.1 degrees. And as we've already seen on our chart here, angle number 3 and angle number 4 equals angle number 1 plus angle number 2. So if we add those two angles together, 57.9 degrees and 7.1 degrees, that gives us a sail angle of 65 degrees. So all of this means that we have chosen 800 feet for our kickoff point. We're going to build at 3 degrees per 100 feet to 65 degrees, and then we're going to hold 65 degrees to the target, and we will hit it as planned. Okay, the next section that we're going to review is looking at multiple well target well planning. Multiple well planning will be described through the application of an exercise which purposely contains multiple targets that causes us to do the analysis and planning steps to come up with a directional strategy that satisfies the directional requirements. So it's much better to do this with an example and to go through an example than to try to put it into fancy words. Okay, we're going to be starting off in which most of the time this comes from a geologist or someone in the geoscience aspect of our organization, and they're going to give us well planning target objectives, something like this. And it says develop a drilling directional drilling strategy in order to meet the well target objectives listed below for an offshore well. Assume an RKB of 100 feet for preparing the directional plan. The geologist probably will not tell you this 100 feet RKB, but based on experience in the area and the type of rig that you intend on using, you will probably select your RKB. But for this example, we're going to use a 100-foot RKB. So you can see from this diagram that he gives the TBD of the 5 targets is 5 TBD depth subsea of 5 targets. The distances from the north line and from the east line or west line of the blocks are shown here. So I can tell a little bit by looking at this information here. It says the surface location is located 10,022 feet from the east line of Eugene Island Block 126. The first target is located 10,906 feet from the east line. So just by the fact that I can compare that value and that value, I can tell that this well is getting farther west from the east line. So therefore this well is being drilled generally to the west. I also can look over here from the north line and I can see this well is getting farther from the north line. So it's going in the southern direction and it's going into the westerly direction. So the first steps we need to do is to get our grid information for where we're operating in Eugene Island 126. So that's going to be, get that off of a protraction map. So here is a protraction map of Eugene Island area in the Gulf of Mexico. You're not going to be able to see these blocks, but if I were to expand it, these blocks would be located right in here. There's 3 blocks included into this project. Blocks 126, blocks 141, and block 140. So this forces us to evaluate our grid, horizontal grid, and to calculate our value. So if I blow up this map and only take these 4 blocks, here are our Y and our X values for blocks 126, 141, and 140. All of our project, either surface locations or targets, are located within these 3 blocks, 126, 141, and 140. So I can take this information and then I can construct a table in which we're going to chart and we're going to calculate the TBD from a project perspective. What is the TBD from a project perspective? We're going to calculate the distances south of each target. We're going to calculate the distance west for each target from the surface location. We're going to calculate the total displacement of each target. And of course, as we've already seen, the displacement is going to be the square root of the sum of the squares of the west component and the south component. We can calculate a change in displacement between each target. We can also calculate a change in TBD between each target. And then we can calculate a direction from the surface location to each target. And then we can calculate inclination between each target to see how they are aligned in space. So you can draw each target if you want to, like this. Here's a plan view. So this well is going to the southwest, and you're going to have a west displacement, and you're going to have a south displacement, and you can calculate this angle here of the direction, I call it from the south. And then likewise in a vertical section view, you're going to have a change in TVD between targets, and you're going to have a change in displacement between targets, and you can calculate this angle between targets, the inclination angle between targets. So here is I call it a step-by-step process in which we will follow. Of course, the first step is to complete this chart and compile all the distances and the angle changes on it. The second step is to select a sail angle needed at target number 2 in order to hit targets number 2 through 4. And then step number 3 is to determine the inclination angle required at target number 1 in order to have a continuous build between target number 1 and target number 2. I won't continue to read the following steps because it's an example that we're getting ready to do, but I've got them listed there for information just so you would have it as your reference. And we're only going to need to look at, I call it basic equations that we've already used and done an example of to calculate our vertical distance while we're building angle, horizontal distance while we're building or dropping angle, and then the build rate needed between 2 targets when we know the change in TVD and we know the 2 inclinations that we need at the 2 target locations. So you can take the protraction map for block 126, and I've just done this for illustration, and you can subtract, if you subtract the x's, you will find that the distances east and west for all 3 of these blocks are 15,022.16 feet, and the distances in a north-south direction from the south line to the north line of, say, block 126 is 14,498.58 feet. Now, if you do the mathematics of this and multiply the distance west times the distance north and divide by the square footage in an acre, you'll see that this block comes out to be exactly 5,000 acres. So in other words, many, many, many years ago, the Gulf of Mexico was chopped up into a grid system that made many of these blocks 5,000 acres. And by doing that, it gave the X's and the Y values and in order to just an arbitrary grid system that was set up so that any company could lease Eugene Island block 126, and you would know exactly your operating area, your boundaries that you can operate in and drill a well and say Eugene Island block 126. So we know the distances east and west and north and south. So with these values, and by the fact that I gave the values from the east line or from the west line in the geologist did of these 4 blocks, then we can calculate the value of distances from our surface location and complete our chart in order to be able to continue doing our directional planning. So if we complete the chart, then you will end up with a chart that's going to look like this. So the target number 1 TBD is 100 feet more because I've added RKB to all of the subsea depths to come up with the TBD depths. And then I have gone through the mathematics and calculated all the values that we need in the chart in order to, I call it, make our, come up with our strategy for drilling a well. So the first thing you can recognize on this chart is that if you look in column number 7, all the directions of all the targets from the surface location, it has a direction from the south of 60 degrees. So that means that all of these targets are located going south 60 degrees west. So you also could say that would be a 240-degree azimuth. If we add 60 to 180, that would be a 240-degree azimuth in direction. We also can look at this chart and see that between targets number 2 and target number 4, they're lined up in an inclination of 54 degrees. So it's 54 degrees between target number 2 and target number 3. It's also 54 degrees between target number 3 and target number 4. And it happens to be 39 degrees between target number 1 and target number 2. And it's 33 degrees between target number 4 and target number 5. So there's some basic information that just shouts to us when we look at this. This information to me shouts that when we get to target number 2, we want to have an inclination of 54 degrees at target number 2. So then the next steps, if we look at, look at our chart, and we can do this by plotting the angles, or we can just do it by looking at the information. If we look at a plan section view of this information, like I say, we can see that an inclination between targets number 2 and targets number 4 is set at 54 degrees in order to go from target number 2 through target number 3 and to target number 4. All right. Now, based on the circular properties for tangents to a chord, the difference, this angle is 39 degrees. So it's 39 degrees, and this inclination is 54 degrees. So that means this angle is 15 degrees. So based on the circular properties of tangents to a chord on a circle, then the inclination at target number 1 needs to be 15 degrees less than this chord inclination of 39 degrees, which would be 24 degrees. And then likewise, down at the bottom, this is 54 degrees, and the angle between target number 4 and target number 5 that we looked at on the chart was 33 degrees. So therefore, this change in angle is 21 degrees. 54 degrees minus 33 degrees is 21 degrees. So if we subtract 21 degrees from our inclination here, then we will need 12 degrees at the bottom in order to have an average angle between target number 4 and target number 5 of this 33 degrees. So the bottom angle needs to be 12 degrees, and our top angle needs to be 24 degrees. Okay, so we know all the angles that we need at each target, so we know that. So then the next step is to choose to calculate our kickoff point for the well and the rest of the information we need to come up with our strategy. So we need to determine the build rate between target number 1 and target number 2. We know the change in TVD. We know the two angles of 24 degrees and 54 degrees. So we have all the information that we need to calculate the build rate. If we plug those values into the build rate equation, we'll get a value of build rate of 2 degrees, which is acceptable for a rate of change in inclination. So that should fit a real project with no problem, should not be an issue. Then we need to calculate the drop rate between target number 4 and target number 5. Going through target number 5, we're going to go from 54 degrees down to 12 degrees. So, all right. So we need a 12-degree angle at the bottom. All right. In order to do that, then we'll use the same equation. We put sine of 12 degrees minus sine of 54 degrees with the change in TBD, and we get 1.5 degrees, which is an acceptable rate of change in inclination between target number 4 and target number 5. So we know the two angle changes or build rates that we're going to use between target number 1 and target number 2, and target number 4 and target number 5. So a build-up rate of 2 will be utilized between target number 1 and target number 2, since we're going to use I call it, that's the rate that we calculate, and we're going to use a 1.5 degree drop rate below target number 4. Now, since we're going to use an angle change of 2 degrees between target number 1 and target number 2, it would behoove us to use the same build rate change above that, up the hole above that, where our kickoff point is, in order to go to target number 1. So if we do that, then we need to determine the kickoff point for the well based on using the same 2-degree buildup rate. So if we use the same buildup rate, then the radius using a 2-degree build rate is 2,865 feet. The vertical depth that it is going to take in order to build angle to 24 degrees is going to be the 2,865 times the differences in the sine between 24 degrees and 0, which is 1,165 feet. The displacement that it's going to take to go from 0 degrees to 24 degrees, using the same equation, which we've used several times, is 248 feet. So then the additional displacement that we need, looking at our chart, we need 1,021 feet of displacement at target number 1. So if we subtract 248 feet, which we get by rebuilding angle, means that we need to get an additional 773 feet while we're holding angle. In order to calculate that vertical depth while we are holding angle at 24 degrees, it's going to be the 773 feet divided by the tangent of 24 degrees, which is 1,736 feet. So now we can calculate our kickoff point for the well, which is going to be the total vertical depth at target number 1 minus the vertical depth while we're holding angle minus the vertical depth while we're building angle. And if we take these values of 7901 minus the 1736 that we just calculated minus the 1165 that we calculated here, gives us a kickoff point of 5,000 feet. So now we have all the information we need to write down a strategy. As a matter of fact, it's not very many steps to this strategy that if you could use Siri on your iPhone and stand on the rig floor, and if Siri could speak and talk to the downhole motor and tell the downhole motor to make changes as you go along, it would not take very many steps to execute this profile, which goes through each of these targets. So this would be our strategy that we have just determined all of these values. We're going to drill vertical to a kickoff point at 5,000 foot TBD, holding angle of 0 degrees. Step number 2, we're going to be beginning at our kickoff point of 5,000 foot TBD. We're going to build 2 degrees per 100 feet in the direction of south 60 degrees west, or 240 degree azimuth, to an inclination of 24 degrees. So we're going to build 2-degree build rate from 0 to 24 degrees in the direction of a 240-degree azimuth. That azimuth of 240 degrees is held to the well's TD. There's no changes needed in azimuth at all. Step number 3, once we've got 24 degrees achieved, we're going to hold 24 degrees inclination to target number 1, which is at 7,901 feet TBD. So now we have just arrived with our bit at 7,901 foot TBD, and we've hit target number 1 as planned. Now we're going to do something a little bit different. We're going to, step number 4 is we're going to be beginning at target number 1. We're going to begin building 2 degrees per 100 foot to an inclination of 54 degrees at target number 2. So between target number 1 and target number 2, there's a build rate all the way between 24 degrees and 54 degrees, and then we will hit target number 2 as planned. Okay, so once we reach target number 2, then we hold that angle. So step number 5 is we hold 54 degrees from target number 2 all the way to target number 4. So we hold 54 degrees from target number 2 through target number 3 to target number 4, which is at 13,344 feet TBD. Once we get to target number 4, then we begin to drop. So at target number 4, we begin dropping at 1.5 degrees per 100 feet to an inclination of 12 degrees at our target number 5, which is our lowermost target, at 15,640 feet. You can put this steps into a directional well planning spreadsheet, which I've got multiple copies of different ones, and you will end up and you will get a plan that exactly meets our criteria. So we have 5 targets on our directional plan here, and we have kicked our well off at 5,000 feet. We build up to 24 degrees. We main 24 degrees to target number 1. Then we build at 2 degrees per 100 feet to 54 degrees at target number 2. We hold 54 degrees from target number 2 through target number 3 to target number 4, 54 degrees, and then we drop 1.5 degrees from 54 degrees down to 12 degrees at our lowermost target. And we've met the objective of a multiple target directional plan that was, not too difficult to arrive at. So just want to wrap up and summarize all the information that we have examined on, I call it directional planning overview. We have described some of the limitations of directional drilling. We have evaluated the vertical depth and horizontal reference systems that are utilized for doing directional work. We have reviewed the definitions and references for directional inclination and azimuth. We've described the arc that is necessary for doing directional work and how to calculate the radius of that arc when we do directional work. We've examined the basic directional planning equations and geometry concepts that we need to know in order to do directional planning. We have reviewed the geometry of a circular arc and the tangent angles to a chord on a circle. That's very useful for making inclination angle choices and doing a project. And then we have seen and utilized the steps necessary to develop a directional plan to a single target for 2 different applications. One is when we choose a build rate and inclination, and then the second is when we choose a kickoff point and a build rate. So both of those are for a single target. And then lastly, We concluded by assessing the process to develop a directional plan for multiple targets, utilizing an application example to show how a multiple target directional plan is created for a project. So I hope you've enjoyed these videos, and good luck on your directional drilling and your well planning.